Welcome back to Multigrid Methods. We're trying to get through Chapter 7, which is discussing cell-centered finite difference methods and multigrid solvers for those methods. So we're in slide deck 2 of 3, and we're somewhere in this section called the Alpha-Weak Approximation Property, which we're trying to establish for the cell-centered finite difference method. The idea is we cannot establish the usual strong approximation property. The best thing we can do is get this alpha-weak approximation property with alpha equals a half. So that's what we're aiming to do. Alpha-weak approximation with alpha equals a half. So let's jump forward to that section. So last time I argued that we could reformulate our problem in two different ways, I guess. The first way is instead of thinking about the cell-centered finite difference problem, which I guess we can write in approximation form like this. We have some finite difference version of the Laplacian operator, and we're looking for a grid function UL that satisfies this equation given FL. Now, either we can do one of two things. We can build the boundary conditions into the finite difference operator, or we can just demand that our solution comes from a space of solutions that have the homogeneous Dirichlet boundary conditions attached to them, which is represented like that. So we're looking for UL, a grid function, which satisfies this equation, where this is, I may not have used this notation quite yet, but this is our notation for the discrete Laplacian operator. In one space dimension, this is what we call the 3-point stencil. Now, what I said was we could, of course, we showed earlier that that could be transcribed as a matrix problem, AL UL equals FL. And the way we did that was the way we usually transcribe finite difference problems into matrix vector problems. Now, what we did last time, and what we want to do for various theoretical reasons, is convert this problem into a problem that can be viewed in the space or setting of piecewise constant functions. And if we do this, then this gives us a variational structure and a way of proving this alpha-weak approximation property through what are called approximation or convergence results, approximation results more generally. And these are kind of well known in the setting of the cell-centered finite difference. It's known that if you really want to do analysis with these things, it's better to use this space of piecewise constant functions for various reasons. Now, we can't go into all the depths and details of why that's so. And so we're simply going to assume that, that's exactly what has to be done for our analysis. So we convert this into this variational problem over spaces of piecewise constant functions, where this FL, okay, FL object, we could replace that with FL, is just the projection of F into the space of piecewise constant functions at level L. Now, if we convert that into a vector through the basis, we're going to call that vector FL, okay? And if we have this solution in the space of piecewise constant functions in the basis BL, the canonical basis for the piecewise constant space, we can extract its coordinates and we can call that a vector. And what we said was that those two vectors satisfy this matrix equation where this AL is our standard stiffness matrix. This is the stiffness matrix that is a little bit weird because it has those 3s on the first and last positions of the diagonal and 2s elsewhere. All right, so this is the transformed or reformulated problem that we want. This is the one that we started off with. We saw this already, and this is the new guy. Now, I will say, when you get this matrix vector problem and you get this matrix vector problem, it looks like they're exactly the same thing. They're not exactly the same thing, and that's because the way of deriving this function f is slightly different in these cases. Okay, it's a little bit analogous, where it is analogous to what was done for the finite element case, where the right-hand side for the two problems was different between the standard finite difference and the standard finite element settings. In any case, the most important part is you get this this matrix coming out. That's the most important part. All right, now, a rather famous paper, or at least famous in the setting of cell-centered methods, showed that you can derive a sort of error estimate for this approximation in these piecewise constant spaces. The idea is, let's start with a variational formulation of our original problem. So let me remind you, what is the original problem? It's minus u double prime equals f in the domain omega equals 0, 1. And we also are going to demand that u at 1 and 0 is equal to 0. So those are the so-called boundary conditions. And this is called a boundary value problem. This is our sort of classic boundary value problem in one dimension, called the Poisson problem. So the variational formulation of that problem is given here, and I showed you how to do this way back in chapter 6. Well, let's assume that UL and VL is the unique solution to our new reformulated problem, this variational problem. Notice how the new approximation problem has the same framework as the original variational problem. It's just that the solution for the variational problem is this space H01. Now, for our variational problem over here, it's not like the finite element setting, because VL is not a subspace of HL, or H01, sorry. VL is not a vector subspace of H01. It's just not. So how do you derive error estimates in this case? You can't use Say's lemma or anything like that. You can't use the standard finite element setting. You've got to use some new and additional machinery. And this theorem is rather complicated, which is why we didn't go into it. And it says this: so if I know that I have a solution to a weak solution or a unique solution to 8, my piecewise constant approximation, I'm going to call that my cell-centered approximation. Then what I'm going to do is take my true solution of this problem, and I'm going to project it using the L2 projection into VL. All right, I'm going to project that guy down into VL, and now I can actually subtract these two things. That makes sense. So I'm going to subtract these two functions, and these two functions are both in VL, so their difference is also in VL. Now, stuff in VL, namely this guy and that guy, can be put into this bilinear form AL, which we defined way back somewhere around here. So back here in 4. So we define this thing called AL. We can put both of those things inside of AL, and that's like an inner product. If I put the same thing in the first and the last position, that becomes something like a norm. Actually, it is a norm. So what we're saying is the norm of that difference, UL, and not U, but its projection into the space VL, is less than a constant, which is independent of L, times HL, that's the size of the mesh on the level L, times the L2 norm of F. So this is about as good as you could ask for, because if I look at the finite element setting, I have the same sort of order of accuracy. The finite element setting says if you measure the error UH minus U in the energy norm is H01 norm, then that's less than CHL. Let's see, I don't want to call that H, I'm going to call it UL, HL, F, L2. Actually, what usually appears here is U double prime L2. But it's the same thing as the norm of F. So that's the same order of accuracy. You just get first order accuracy when you measure the energy norm of the error. So that's about as good as we could expect. We can't do any better. Now, we might be able to gain an extra order of accuracy if instead of using the energy norm here, we use the L2 norm of the difference. And so I'll leave it to you to look into that question. Can you improve the order of the error? In other words, could I show something like this, that I get UL minus QLU L2 less than CHL squared F L2 0 1. So let me be quite honest with you. I don't know if this is true or not. I think it is. I think you can improve this order of accuracy by going to this less weighty norm in L2. Okay, so I'm going to leave it to you guys to look into that. I believe it's true, but I'm not going to bet my life on it. All right, so this rather famous theorem is by Ewing, Lazaroff, and Vasilevsky from 1991 when I was in high school, and maybe some of you weren't even born back then. But it's a rather famous paper, at least in the cell-centered multigrid community. All right, now I want to define something called the discrete cell-centered Ritz projection. We defined a Ritz projection in the finite element setting. And if somebody raises their hand and says, I want to see it, I'll do it, but otherwise we'll just assume that you know that one. So here's the discrete cell-centered Ritz projection in this cell-centered setting. So the idea here is I start with some VL in capital VL, and I want to somehow push it down to a VL minus 1 in VL minus 1. There are lots of ways I can do that. So we already know that we could do a basic restriction operation, and that could push it down. That turns out to be exactly the same thing as the L2 projection. So the L2 projection of this object is just basically a restriction. I could also do something called this discrete Ritz projection. So I could use this operation to get an approximation of this guy in this space. All right. So let's see how that's done. Let's see how it's defined. Well, let's let little l be between 1 and capital L. And this is the operator that we're going to define, the L minus 1 Ritz projection. And it's going to take a function, VL, or VL in VL, and it's going to push it down one level. And it's going to do it as follows. Given VL in capital VL, then this object, which I'm trying to define, is it turns out it's the unique object which satisfies this following property. So there's a unique object which does this. It's going to satisfy whatever the heck this guy is, and I can give it a name. If you don't like the fact that this is something else, something complicated looking, I could just give it the name VL minus 1, right? And I could just replace that object with that single function in this piecewise constant space here. So if you don't like that long name, you could use this shorter name. But in either case, it is what it is. It's a function in the piecewise constant space VL minus 1. And it satisfies that if I put this guy here, then it equals to AL VL for every WL minus 1 that I put in the second position in both locations. The first thing we want to make sure is this object makes sense. So we have to ask ourselves, is it well defined in every position? Let's first answer the question, does this guy make sense? So for AL minus 1, I need these functions in here to be both from VL minus 1. So I need this guy and that guy, both of those, to be in VL minus 1, capital VL minus 1. Well, by definition, this is what we call a test function, and that is in VL minus 1. We're looking for this object. We don't know what it is, but we're claiming that it's in VL minus 1. So be it. We'll say it's in there and it's fine. All right. We're looking for that solution. So it's we're defining this thing to be in that space to begin with. Now, what about these guys? For this one, for this operator on this side, we need both of these operations, or so both of these functions to be in VL. So I need both of these objects to be in VL. Both of them, right? So let's see. So the first thing is in VL by supposition. The second thing is not in VL directly, right? It's in VL minus 1. But remember, for these piecewise constant functions, these form a nested space. So VL minus 1 is always a proper subspace of VL. How do I know that? Well, this object is working with a coarse grid, and this is working with its fine grid, right? And so let's just look at what a function might look like on this space. So let's do a very basic grid that has only two intervals for L minus 1. Then these are piecewise constant functions, right? So there's a typical element in VL minus 1. Here's the question. Isn't that also in VL? And the answer is, yeah, of course it is. Because I can add that grid point here and here. And now all I have to do is say what that function looks like that's in that space. What's the natural inclusion? So I just take that function to be like that. And I'm going to take the next piece to be like that. Next piece like that. And then the next piece is going to be like that. So I hope you see that the function I just defined is a function in the fine grid space VL. It's defined on 4 different intervals, right? And it's this piecewise constant function. Well, it just so happens that it's constant over these 2 adjacent intervals and constant over these 2 adjacent intervals. It doesn't change. But it's clear in any case that this function here is in VL, no problem. Okay, every test function is in VL. That's good. So the whole thing makes complete sense. If I ask, is there a function such that when I test it against WL in the AL minus 1 inner product is equal to the function, the original function tested against WL minus 1 in the AL inner product? And at least everything in that question makes sense. So I could show you that such a thing exists and is unique. Okay, such a thing as this object we're asking for, RL minus 1. So this is a script RL. So I'm going to put a little dressing on it. VL exists and is unique. That's good. Right? Because if I ask for something and make a definition involving something, I want it to be there whenever I need it. Of course, I want it to be well defined. I want it to exist, and and ideally, I want it for it to be unique. All right, so that's the thing called the Ritz projection. It satisfies that definition. All right, so assume that. So now we need a little. We kind of are going to prove that it exists and is unique via a kind of alternate approach. So here's how we're going to do this. Suppose that L is between 1 and capital L, and VL is some given piecewise constant function in capital VL. Set VL minus 1 to be equal to that Ritz projection of VL that we said should exist by the previous definition. Now, under the usual coordinate identification, what I mean by that is this object that we want, we're going to identify with this vector VL minus 1 through the basis BL minus 1. That'll be a vector in RNL minus 1. And I'm going to identify the starting function, the starting piecewise constant function VL, with its coordinate vector through the basis BL. So these two bases aren't the same. They're in the same family of bases, but they're not exactly the same. This one lives on L and this one lives on L minus 1. So these are just the coordinate vectors. Then the coordinate vector for this object here, which is what I want, is exactly equal to the pi L minus 1 matrix times VL. So this is wrong here. I changed this in the notes, but I forgot to change it in the slides. So this guy is not called the coarse grid rich projection. So all I can say is that this matrix is defined. So where this matrix is defined, I should say as before. I believe I fixed this up in the notes, but kind of a little sloppy here in the slides. So let me make a big note for myself so that I can come back and fix this. So where this matrix is defined as before by this. All right. So this is kind of related to the coarse grid risk projection. You'll recall that the coarse grid risk projection matrix actually is pi L tilde, and that's going to be PL minus 1, AL minus 1 inverse, RL minus 1, AL, or in other words, it's just going to be PL minus 1 times that matrix pi L minus 1. So this guy here is square, and this guy here is not square. This is what we called the coarse grid risk projection matrix. This had no name. I couldn't figure out a good name for it, so I called this the coarse grid risk projection matrix. Remember, that's the para matrix, the para matrix. So if you speak a little bit of Greek, this means with. I'm not sure that helps you remember the name, but para. This matrix here is non-square, and I had no good name for it. In any case, if I have this matrix lying around, this non-square matrix, then if I multiply it times VL, I get the coordinates of that coarse grid risk projection. That's pretty cool. Okay, that's pretty cool. So that says where the coarse grid risk projection, kind of what it is in terms of matrices and vectors. And you'll notice that that's pretty similar to what we had in the finite element case. All right, so let's try to prove this. So how would we go about a proof for this? So um, by definition, what we can do is we can take our coordinates and put those in the definition for the coarse grid risk projection operation. Remember the coordinates we said of this object VL are just these coordinates of the vector VL, vector VL. And if we had this identification with the given vector VL, then this is going to be the basis representation of that function. Now, like before, anytime we have this property posed over a finite dimensional space and it's linear, I can replace these objects in here, these test functions, by basis functions. And that's all I'm doing here. I'm replacing those test functions by basis functions. So I know that it has to be satisfied for every basis function in my BL minus 1 basis. So in other words, for every j from 1 to NL minus 1. Now just notice this is AL, this is AL minus 1, okay? Now let's do a little bit of work on the left-hand side of 10. So let's look at that guy. What do we get here? Well, we know that 10, or the inner product in 10, is linear, so we can pull out some objects. We can pull out this guy and that sum. So the sum comes outside, and so we just get the sum I from 1 to NL minus 1 of VLI, those coordinates. Now we just have AL minus 1 against or involving two basis functions from level L minus 1. Well, we said a property going pretty far back, I guess, 5, said that, I'm not going to touch on that because it'll flash back to it, that object there is just HL minus 1 times the element in the ith row and jth column of AL minus 1. Now remember that matrix is symmetric, so it doesn't matter if I have I here or J here, they can interchange, no problem. But I do get a factor of HL. Right. Okay, so that tells us what this object is in terms of a matrix times a vector, or at least the coordinates of a matrix times a vector. Now let's operate on the right-hand side of 10. So keep this in your back pocket for a minute. HL times the jth coordinate of AL minus 1 times the vector VL minus 1. Now we're going to observe that the way our prolongation matrix was defined was in such a way that I forget whether we actually, I think we did show this, but at least if we didn't show it, convince yourself of that if I take the basis function in the space L minus 1, let's take the jth one, then that is just a linear combination of basis functions in level L, okay, or BL, the basis BL. So any basis function BL minus 1 can be expanded in the space of functions, well, in the basis from VL, which is called BL. So why is this true? It's true because each one of these functions is in VL. Remember, if you do it in two steps, first of all, we recognize it's definitely in VL minus 1, and this is a subspace of VL. So of course it's definitely in VL. I guess it's a proper subspace, so we can remove that. So obviously any function from that space has a basis expansion in that space, and that's all I'm doing. And then these coefficients are just equal to the elements of the prolongation matrix. So in other words, the element of the prolongation matrix PL minus 1 in the S row and jth column is just equal to that object there. Now, remember, this matrix is a tall and thin matrix. It has more rows than it has columns, and so that all makes sense. So now we're going to take this guy and we're going to plug it into the right-hand side of 10. So in the right-hand side of 10, we had that basis vector there. And so now what gets plugged in there is that object. Okay, cool. Now, what we can do with that is we can use the linearity of AL and pull out two sums. Okay, so a sum from K equals 1 to NL and a sum S equals 1 to NL. And we pull out all of these coefficients here. And then what we have remaining is just this object. Now, again, this object is related to what we a little property that we showed before. This is just going to be HL times the KS coordinates of the matrix AL, or in other words, the element in the kth row and sth column of AL. And again, I can interchange those two things because this matrix is, of course, symmetric. No problem there. All right, now, what is this object here? This just turns out to be PL minus 1 transpose times AL times VL and the jth entry of that vector. So I'll let you prove that to yourself. But if you believe that, now we have a new representation for the left-hand side of 10 and the right-hand side of 10, so we can set those two things equal. So if we set those two things equal, so it's going to be this guy equals this guy here, right, for every j. So that says, since it's true for every j, that AL minus 1, VL minus 1, I'm going to just move one of those h's over to the other side. The one that was on the left, I'm going to move to the right. Okay. And so that just gives me a 1/2. PL minus 1 transpose, well, let's hold on to that for just a second. AL, VL. What is 1/2 PL minus 1 transpose? Though that is just exactly equal to the restriction matrix. Remember, that's this weird new thing that we're doing in this section that was different from the finite element setting. In the finite element setting, we always wanted to have the restriction matrix equals to the prolongation matrix transposed. Restriction matrix equals to the transpose the prolongation matrix. Cell-centered finite difference, we said, no, we don't want this anymore. We're going to take that to be a half for whatever reason. Well, the reason is because we can actually prove convergence for that. We can't prove convergence for that one. In any case, that's just the restriction matrix times AL times VL. So now just set everything equal to each other. We'll move this guy to the other side. So that's AL minus 1 or AL inverse, RL minus 1, AL VL. And so that's just the pi L minus 1 matrix. Remember, I was mistaken when I wrote this up the first time. That guy has no name. It's just that object. Non-square rich projection matrix. Okay. So we proved that last result. So that says, what this says is that this new object that we call the coarse grid or the cell-centered rich projection is not really all that exotic. It's just related to a matrix that we already know and love, okay? So it's not exotic. As long as we make these coordinate identifications, then we have this. Now, here's the thing. This guy is always solvable. All right. So in a way, this is proving that this object exists and is unique. This guy is always uniquely solvable. And so it tells you that this object that we conjured up actually exists and is unique. So I don't like, so if I had to do this proof again, I would say that this problem is equivalent to this problem. And since this problem has a obvious solution, and a unique solution, then this problem has an obvious unique solution, and therefore it's well defined. But I kind of got a little bit loose on that. But if you want to think about it in a certain way, I've just proven two things. I've proven the identification with a very familiar object, this pi L minus 1 matrix, and I've also shown that this coarse grid Ritz projection operation is actually well posed. Makes sense. Okay. Now I wanted to find something else called the lifting operator because it's going to be something that I need. Actually, I thought about saying or redistributing things. Maybe the lifting operator should actually been put into that section more some additional multi-level tools. I kind of couldn't figure or decide whether I should put it there or leave it here. Still up in the air. But in any case, it's something new that we need. And it's a little bit weird, and maybe you need to think about this a little bit. What a lifting operator does is it takes something from my finite dimensional space and it's going to move it into my continuous space or my smooth space, quote unquote. So let's let L be between 0 and capital L. Then this lifting operator is going to lift us out of this space and into that space. And it's defined as follows. If you give me a function in the finite dimensional space, piecewise constant, then it's lifting LVL in this space. This is my Sobolev space that, remember what this Sobolev space is the space of all weakly differentiable functions that are also L2 and that have zero boundary conditions on the domain 0 to 1. Zero Dirichlet boundary conditions. So it lifts this discontinuous function, okay, piecewise constant function into this space. And it's the solution of a variational problem. Okay, it's the solution of the following variational problem. It's going to be, let's for a second, let's just give this a new name. All right, let's call it V. Okay, So really this is just going to be V prime. If I say V equals LVL, right? Then this is just V prime, W prime. And W prime is going to be a test function. And that's going to be equal to some function. Hold on for the definition of that for just a second. Some function against the same test function. Now, all that we need for this function to have a solution is for this function here to be an L2 function. So let's think about what is this guy here. This is the finite difference operator acting on this piecewise constant function. So we defined this someplace else. This is really all that you do to calculate this thing. Let's see, where did we define this? So to define it here, uh, yeah, we defined it right here. So how could I apply a finite difference operator to a piecewise constant function? Well, you just take the matrix AL and you multiply AL times the coordinates of that vector, and then you take that vector of new coordinates, and you're going to use that to expand in a basis expansion involving the basis elements from BL. So that's how I define this object minus delta L circ, minus delta L circ. So that's supposed to be evocative of the minus Laplacian operator. It's actually a discrete operator because it acts on discrete functions. Okay. So if I can act on discrete functions with this operator, that just gives me something back in the space VL. All right, so that's in VL. Remember I said all we need for this thing to be well defined is this object here has to be in L2. So the question is it in L2? Answer yes, because VL is a subspace of L2 functions. All right. It's not a subspace of H1 functions because H1 functions have to have a certain smoothness. They have to have their first weak derivatives existing and being L2 functions, which objects in this space do not have. Objects in this space have what's called a distributional derivative. So its derivatives are delta functions, actually, just something called a distribution. You may have seen this concept in Math 547. Probably not have seen it in our PDE courses, unfortunately, but you may have seen it in 547. You can ask Dr. Mengesha to tell you what that's all about. But suffice it to say, this object is an L2 function. We're good to go there. So this is just a Poisson problem. This is just a Poisson problem. So let's highlight that. This is just a good old-fashioned Poisson problem. Good. So an object like that always has a solution. Actually, it's a weak formulation of a Poisson problem. So I called this unknown thing here V, but that's actually the lifting operator. I'm acting on the lifting. And why am I saying it's the lifting of VL? Well, because VL appears over here. So it's involved in the definition of this object. So it's actually taking this piecewise constant function and it's pushing it up to this space. Now, how do I know such a thing exists and is unique? Well, I just said, as long as this object over here is an L2, then this is just a Poisson problem or a weak formulation of the Poisson problem. And every Poisson problem that is of this form has a good and true solution. Okay, so such a thing always exists. The next thing I need to do is give a stability result for this lifting operator, which we're going to need later on. And it says this. So for every VL in VL, capital VL, if I look at this lifting operator of that object, remember that we said that that object is going to be something which is smooth. So this is kind of like a backward stability. Um, we'll see how it's proved, but it's kind of, in my mind, it's kind of like a kind of a reverse stability. Usually, what a stability says is that if I take something from a high dimensional space and push it down to a low dimensional space, then the low dimensional space object is bounded by some norm of the high space dimension object. This is different. I would call this like maybe backward stability. I'll ask Abner what he thinks about this. Backward stability. I don't know. It's not the usual normal forward stability. Let's just put it that way. So for every one of these guys, there exists a constant that should be independent of L, I believe, times AL, VL against VL. So this is like a norm squared, and this is a norm squared. I think I said that wrong. Let me say the lifting of VL in the H1 norm squared is less than a constant times the norm of VL in this new energy norm, this discrete energy norm. Okay, so this one I didn't want to leave to chance, so let's prove that this is true. All right, by the Poincare inequality, there is a constant C1 such that this holds true. All right, what's going on here? If you remember what the Poincare constant says is that, or Poincare inequality says, you might have seen it as like this. So it's saying something like, generally speaking, that there's a constant such that the H01 seminorm of V is greater than the L2 norm of V. And sometimes people put the Poincare constant over here, and other people like to put the Poincare constant over here, and some people like to introduce Poincare constant with squares. But in any case, now why does that inequality lead to this inequality here? Well, that's because what we can do for this guy is if we use it as the square, we can add the H1 seminorm to this side, H1 seminorm squared of V, and we can add the same H1 seminorm over here, and we're going to get CP plus 1 times that same seminorm squared. And over here, we're going to get the full H1 norm squared. So the Poincare inequality tells us that the H1 seminorm beats, or with a constant, can beat the H1 full norm of any function, as long as it's a smooth function. So here, what is the smooth function we're going to use? We're going to use the lifting of VL. That's going to be our smooth function. So this Poincare constant might be CP plus 1, I guess. Now we're going to use the definition of the lifting operator and the L2 projection operators. Okay, and we're going to use the stability of L2 projection that we've used before. Now, by the definition of the L2 or of the lifting operator, remember that guy is defined here. That's just a variational formulation of a particular type of Poisson problem where the F is that guy there. So that's my forcing function F. Just has to be L2. Okay, so that's the definition. So now if I use as a test function the same function here, so this is like saying in here I'm going to use the same function W as a test function as I'm going to use as the solution. That's fair because if you can prove that something like that exists, then it's going to appear in the test space as one of the possibilities, and so you could use that the solution as the test function. So put that there, and it also goes there. All right, now what do we know about this function? It's a smooth function. That's a smooth function. This function here is a piecewise constant function by definition. And so by the definition of the L2 projection, I can replace this object with its L2 projection. Why is that true? Well, if I remember, QL, come on, QL, let's see, I'm going to just use a generic F. So that's the definition of the L2 projection of a function f, which is just an L2 function, into the space VL. Now, I can also replace this by basis functions if I wanted. I could just say it holds for all the basis functions, no problem there. But why can I use it in this context? Well, this function here is a piecewise constant function. That's piecewise constant. So the L2 projection is going to satisfy this equation for all piecewise constant functions. So the L2 projection of this object, which is written that way, satisfies this equation for every piecewise constant function, which is what that guy is. So this is true by definition, okay? It's an equality. All right, now for, what does for say? For is our definition of this AL inner product going way back. So if we go back to that, there's how we define that guy. And notice that it involves this object here. Okay, so this is what we called the AL inner product of UL. So that's exactly that object right there. AL inner product of VL, and whatever this object is in the second coordinate has to be in VL. Luckily, we are in VL now because we've taken this thing. So look at what we've done here. We started off with something in VL. We've lifted it out of VL into a space of smooth functions. Then we put it back into the space of piecewise constant functions through this L2 projection operator. Okay, that allowed us to write this object with equality as the AL inner product of VL against QL, L, capital L, script L, VL. Now, let's apply the Cauchy-Schwarz inequality in the last step. This inner product is a good old-fashioned inner product, and we can apply Cauchy-Schwarz to that. Right? So this is just Cauchy-Schwarz. What does Cauchy-Schwarz say? If I have an inner product, two objects, then that its actually absolute value is less than the norm of the first object in that norm arising from AL times the norm of this object, same norm, okay, in the AL norm. And so that's just Cauchy-Schwarz. All right, let's see if we can make further progress to that. We're trying to get this. Well, looks like we have half of it there, but we have, and let's see, this object here is exactly that object, right? So if we could say something about this, then we're going to be done. Well, now, let's see. We're just going to copy down the same thing that we had on the last line, right? Oh no. Let's see. Oh, I did make a mistake. So this object here is not quite that object, right? We have to use our Poincare inequality to get there. All right, so this object is less than C1 times this object, which is less than C1 times that object. So if I use the Poincare inequality, this object is less than C1 times that. Okay, now we need to use the stability of the L2 projection. So what was the stability of the L2 projection? Somewhere back in here. We can blink back to it in a second if we need to. But what the stability of the L2 projection said was that this object here, okay, was less than the L2 norm of, without this piece, just this object, okay? So let's see if I can find that. So it's somewhere about, right here. There we go. It's that statement right there. Okay, so what I'm essentially using here the H1 seminorm. H1 seminorm. This is the H1 seminorm squared, but that's fine. So look, if I take square roots of both sides, square root of both sides, then this is just precisely going to be the object that I'm dealing with at the moment. I want to get rid of this AL and this QL, and this H1 stability of my L2 projection allows me to do that. So I'm going to replace this with that. That's my H1 stability of the L2 projection. Okay, so now what do I have? This object here, that's basically what I want. This object here is just going to be the seminorm of this object. I think I've got a slight mistake here because I've just copied this over as an H1 norm. It's not quite though, is it? What I really need to do is, oh, no, we're fine. We're fine. Why? Because this is an H1 seminorm, and all I'm saying here is that's less than the full H1 norm. Remember, a Sobolev seminorm is always less than its full norm. So I'm okay here. I just forgot to add my inequalities. Now, what do we have? We can take that guy and cancel one of the, well, we don't want to cancel the whole thing. We just want to cancel the square, right? If I cancel that with that square, I have exactly what I wanted. The proof is complete. And what have I used here? I've used Poincare inequality and I've used the stability of the L2 projection. Those are the two technologies that I've used in this case. All right, so let's kind of look where we are. So we have this thing called the lifting operator, which we just defined. So that takes piecewise constant functions, pushes them into the continuous space H01, and we just showed that we have a stability for that. Actually, it's kind of a backward stability. Previous to that, we had this operator called the discrete cell-centered risk projection operator. We showed that that's related to an operator that we've seen before. All right, so we're now amassing all the tools that we need in order to dive into the big theorem here at the end, which is our alpha-weak approximation property. So I'm hoping in the last 20 minutes to finish this. And yeah, if I could do that, then I'm going to be really happy. And then we'll save then the third slide deck for Thursday and the next couple lectures. All right, so this is, if I look back in chapter 5, and specifically in section 5.9, this is going to give me this precisely when I reinterpreted it into matrices and finite dimensional stuff is going to give me my alpha-weak approximation property. And specifically, it's the alpha-weak approximation property with alpha equals a half. Okay? So that's what we're doing. We're proving an alpha-weak approximation property. It's going to be the punchline. Our last slide in here is going to reinterpret this in the very common standard notation that we had from section 5.9. Okay, so let me stop yapping and start trying to prove this. There exists a constant, okay, such that, which is by the way also L independent, such that for every VL in capital VL, AL, oops, that doesn't quite work, does it? I have to change that. That should just be 1. So the one thing I'm doing as I'm going through these notes, and I want you to do the same thing. I want you to do the same thing. When you go through these, you want to say to yourself, does that make sense? Just let's look at the labels and see if there's anything out of whack. So here's how I knew this label was out of whack. If I really do go down if I really do let little l be 0, then this object here would be r0 minus 1, r minus 1, and that has no definition. So we didn't define that. And so we could just define it as being the identity, but for the moment, we're not going to define that object. At least I didn't define it previously, so that it doesn't quite make sense. So we're not going to use that. That's just going to be a basic check. We know that little l should stop at 1 based on our definitions. Okay, AL, inner product of the two functions VL minus RL minus 1 VL. So this is our cell-centered Ritz projection into the coarse grid space VL minus 1. So we're looking at the difference between VL and its projection through this Ritz projection into the space VL minus 1. And we're going to take its inner product against VL. Take absolute value. That's less than this constant, which is L independent, times HL. That's the only real H or L dependence. Well, there's L dependence over here as well, but there's no L dependence in C, let me say. HL times this discrete Laplacian operator acting on VL. Remember, this guy is an operator which takes a piecewise constant function to a new piecewise constant function, and that was defined somewhere in this area. We're going to take the L2 norm of that times the L2 norm, sorry, not L2, but the AL norm of VL. Okay, so we want to show this, and what I'm claiming is, if we can show this, this proves the alpha-weak approximation property with alpha equals to a half. That's easy enough to see once we get this done. So how do we do this? Well, what I'm going to do is I'm going to use a triangle inequality and break it up into three terms, which I can address. I can't really do anything with this term directly, but I can, if I break this up into three different terms, I can do something with that. So what I'm going to do is I'm going to take this VL minus RL minus 1, and I'm going to subtract first QL LVL. Okay, if I do that, then I have to add that back. QL L is the lifting operator, VL. So I've just added 0 there. And I'm going to subtract QL minus 1 LVL. Why? That's a good question. So if I add that, if I subtract that object, let me add it back. And then finally, I have my last object, which was already there. Okay, RL minus 1 VL. That's the Ritz projection. Okay. So notice that we get cancellation here of all these intermediate terms. And so it's clear that I have one thing equaling the other. Now, since this is a linear object, okay, what I'm really using is the triangle inequality of the absolute value symbol. Absolute value symbol obeys the triangle inequality, right? So if I have A plus B plus C, that's less than absolute value of A plus absolute value of B plus absolute value of C. Very basic triangle inequality that I've used there. I'm using the linearity of the first component of AL. The second component of AL stays the same every time. Okay. Now I know that AL is a symmetric bilinear form, has a lot of nice properties, but I can just leave that object in that second position alone. Now I'm just going to relabel these terms T1, T2, T3, so that in the end I have this sum T1, T2, 3, T3 that I have to estimate in turn. And so what I want to do is basically show that each one of these objects is less than an object which looks like that. That's the idea. So each one of these three objects is less than a term, which looks like that, and therefore my proof will be complete. So I'm going to start off with T1. T1. So T1 is V minus the projection of the lifting of VL. Okay, VL minus the projection of the lifting of the thing itself. So let's see, how can we deal with this object? The first thing I'm going to do when I deal with this object is just use the Cauchy-Schwarz inequality. All right, basic Cauchy-Schwarz. So I just have that and that in that inner product. It's going to be less than the norm of the same inner products of those elements broken up. So I could have defined a norm, I suppose, the AL norm. Maybe that would have made life a little bit easier. So I could have defined that script AL norm. The problem is it got a little bit too close to the matrix norm that we usually use, that, or the AL energy norm that is similar to that. So I decided to forgo that. So the first thing we do is Cauchy-Schwarz, and then we're going to apply the error estimate that we had previously. Okay, so what does the error estimate say? Error estimate 9 says that, whatever this object is here, okay, I'm going to take that and project it, okay, project that. And then this is going to be the finite dimensional approximation of that object, okay? So we've done a little bit of a sleight of hand here. Let's see. Yeah. We've done a slight bit of a sleight of hand, I guess. So what is this object, or what is the true solution of this object here? So it just turns out we just need to know what is the right-hand side for this solution here. What's the right-hand side for that solution? Well, remember, that's just the lifting operator. So if we go back to the definition of the lifting operator, that's somewhere about, let's see. I'm going to get there. Here we go. So the lifting operator, what's the right-hand side of that? That's just that thing there. Okay? So now, if we're looking at VL, VL is just the finite dimensional approximation of this guy. So that means that we can apply that error formula from 9 to this object here. Okay, so this is our cell-centered finite difference approximation, and all we have to do is realize that this is a cell-centered finite difference approximation of that lifted function. Okay, so let me write that in words. VL is the cell-centered finite difference approximation of its lifting, of its own lifting. Bam. And the right-hand side for the continuous version, or for the continuous solution, is this guy here. That's the F that we have to use in that error estimate. Okay, so there's a couple of things. The F for LVL is minus that Laplacian operator on VL. Those are the two facts that you have to use to get that guy. That's just from our error approximation 9. This guy doesn't change. Now, for T1, we're done. For T1, we get exactly what we wanted, okay? Does everyone see that? For T1, we're done. So now let's go on to one of the other ones. Let's do T3 first. So we've done T1, let's handle T3 next. So we begin with a preliminary observation. Let's suppose that VL in VL minus 1 is the cell-centered finite difference approximation of this guy, but in this space. In other words, this VL minus 1 is the following unique solution. It's a unique solution that satisfies this approximation. Okay, because this has to be, again, this is just our f function, and this is our weak approximation or weak formulation of our Poisson problem, but it's in the cell-centered finite difference setting. Okay, so this is going to be our finite difference approximation of this function here. And this function, we just need to know what is your f, and the f is precisely that. Now, on the other hand, VL minus 1 is a subspace of VL. So, and by the definition from 4 of our energy form, what we know is that AL, VL, WL minus 1 is equal to this object. So if you go back to 4, you'll see that that's how this guy is precisely defined, but this test function is a little bit wonky. Remember, the test functions here should have been from VL. If I go back to 4, the test functions should have been from VL. And here we're, well, let's look. Is this guy really from VL? Well, normally you would say, no, it doesn't look like from VL because it's got the wrong index, but it's from VL minus 1. But remember, VL minus 1 is a nested subspace of VL. So this is equal to that by the definition 4 of our energy form AL. All right, so we can take this object here that appears on the left-hand side of this equation, and we can replace it by that equation. Now we're going to recall by the definition of the discrete Ritz projection operator that this Ritz projection operator here satisfies this equation. All right. Well, now this equation here, or this object here, is the same thing that appears here. Okay. So now in the end, I can replace this object for that object. Does everyone see that? I can finally, because I have the equality of these things, can finally take this object and move it into that position. Well, that's nice because it gives me AL minus 1 and AL minus 1. Right? So AL minus 1, VL minus 1, WL minus 1 is equal to AL minus 1, RL minus 1, VL, WL minus 1. Both of these are L minus 1s. Well, if this is true for every WL minus 1, then because these are inner products, these two objects have to be equal to each other. This object has to be equal to that. So in summary, this RL minus 1 is the cell-centered finite difference approximation of this function, the lifting operator VL, in this continuous space. And so what that says is now we can again use our error estimate from 9. So what we need to know is, well, what's the left-hand side? The left-hand side for that continuous function, f, is going to be that object there. Okay, and now what we need is this approximation here for, that's something that's eventually going to appear in T3. Okay, that's just going to be our error estimate 9 again. Oh gosh, went back to error estimate 9. Now I've got to remember where I was. Not quite there. Okay, so what I'm doing is foreshadowing. This is the error estimate that I need using these facts up here, but that hasn't appeared yet. It's going to appear down here. Okay, when I use the triangle, or not triangle inequality, but Cauchy-Schwarz inequality on T3. Now, the last thing that I have to observe is that using the imbalanced Galerkin condition, for all WL minus 1 and VL minus 1 that we're going to have this property. Now this is not clear by me just saying it. So I'm going to say this is an exercise. I wish I would have given it as a homework for you guys to try out. It's just a fact that is kind of a little bit of has a little bit of a complication, slight complication, but it just follows from the imbalanced Galerkin condition. And what happens in the imbalanced Galerkin condition? Let me just remind you. Imbalanced Galerkin says that 2 times, or is it? I think it's 2AL minus 1 is equal to RL minus 1 AL PL minus 1. Okay. I've forgotten, to be quite honest with you, and I'm embarrassed to say, I've forgotten whether this appears here or here. I think it appears over here. But that's the imbalanced Galerkin condition is this condition modulo fixing the 2 position of the tube. I believe it's correct here. And it makes sense because it appears again with this L minus 1 here that follows from the imbalanced Galerkin condition. All right, so now what do I have? So I have, whenever I use the triangle inequality on T3, I get this object, which isn't quite this object here. This is from my error estimate, and that's the arguments that I gave here. The error estimates lead to this. But what I can do is, instead of using AL minus 1, right, I can just use AL. Or sorry, I want to switch to AL minus 1. So I'm starting out with AL, but I want to switch to AL minus 1. That's going to cost me a factor of square root of 2. That's it. Once I switch to that bilinear form, then I can use this error estimate based on this argument that I had up here. And this argument requires a little bit of patience, okay, to see. So I'm going to say exercise here as well. So I put those two facts together and I get from this error estimate and this change of inner product, I get that. But that's exactly, again, what I wanted. So this, don't be fooled by this C or this HL minus 1. I can switch that to an HL because HL is just 2 times HL minus 1. So the constant here just changes by this factor, but that's okay. I don't care about the size of those constants, just as long as they are, the whole thing is a constant. So T3 satisfies the same structure. So the only thing left here is to consider T2, the middle term. So T2, the middle term, looks like that. Okay. So now I'm going to take again let's see, why do I have, oh, I see. So this was AL, but you can convert this to an L2 inner product by using the definition of the AL energy form. I'm going to take the Cauchy-Schwarz, Cauchy-Schwarz of both sides here using the Cauchy-Schwarz on L2. So that's just going to give me the difference of these functions here and that function by itself there. Okay, now I'm going to use the triangle inequality. Triangle inequality says that I can insert an LVL here, plus and minus. Okay, so now I just want the difference between the Q and the L2 projection in this continuous function and the L2 projection in this continuous function, same one. So I'm just going to use the error estimate on my L2 projection. All right, times this object, which was this guy here just brought down. Well, what I can show is with my L2 projection, this one is going to have an error which is C times HL, and this is going to have an error which is C times HL minus 1. They could be different C's or the same C's, but I'm just going to use the same one because they're both level independent. And so I just get this object. I can change this now to an HL, and I can use the stability of my lifting operator here. That was 12 to replace this by this. Actually, we argued that was like a reverse stability. Long story short, I get exactly the object that I want for T2 as well. So now T1, T2, T3 all satisfy that same structure. So I add them, all three of those together. Sorry, they all satisfy that same pattern. And so I get that this is less than constant times HL times that norm times that norm. So I've taken up a couple extra minutes. Let me take 30 extra seconds. I sped through this last part. I apologize, but got too chatty earlier. What you can show now with that version that we just proved is that what we've shown is that we have an alpha weak approximation property, property A2, holding with alpha equals a half. So in particular, what we can show is that all of that stuff that we had in the statement of the last theorem translates into this. So that means we have everything we need to ensure the convergences of various multigrid methods for our cell-centered method. So I'm going to stop there. Let me say one more word. So we can now prove that the two-grid method converges. We can prove that the W-cycle method converges. This isn't enough to show that the standard V-cycle method converges. That is a little bit too hard to do. Well, it's actually not known whether it can be done yet or not. It's still an open problem. But we can show at least that the two-grid W cycle, two variations of the W cycle, actually the same variation, the same W cycle converges, but under one proof was a kind of weak proof, and then another one that was a little bit stronger. So we have everything we need to show that we have convergence, at least for the W cycle, and that's it. That we're done. Now all we do is just claim that we use all the material from section 5.9, and we can conclude those convergences that we need. Remember, here we use the imbalanced Galerkin condition with R equals a half, and now we're going to apply the alpha weak approximation property with alpha equals a half. We know that we're going to use the lambda Richardson smoother, and that one satisfies the first smoothing property, so we have everything that we need. So I'll end there, and that concludes slide deck 2. You can turn your cameras on, and I'll take any questions you have.